breaking news. This is Jury, and this summer she's been working on something wild at NYU's Composite Materials lab. She's designing materials you have to build from scratch. They're called metamaterials. Sounds fancy, huh?
But really, they're just materials with special internal shapes and the same chemical composition. By rearranging the internal geometry of a metamaterial, we can make it more stiff, more squishy, more flexible, whatever you can imagine. But here's the tricky part about it. Imagine wanting to bake the perfect chewy cookies, but you don't know the recipe. What would you do? You would start by guessing the recipe, testing it, tasting it, and maybe burning a few batches along the way. It's the same with designing metamaterials, except with way more math and way fewer cookies.
Well, Jury had a better idea. What if you taught a computer to figure out the recipe? You tell it what kind of cookie you want, and it figures out the ingredients.
Yeah, so we use something called a convolutional neural network and a Fourier neural operator inside a variational autoencoder.
Whoa, slow down, Professor. What in the world is a furry Oreo operator?
It's Fourier neural operator, but okay, let me explain this the easy way. Starting with CNN, which is the convolutional neural network. It's just like giving a really good pair of eyes to the computer. So it can look at a bunch of images and then spot patterns or textures, just like how we recognize faces or letters. Then we have the variational autoencoder, or the VAE. Think of it as the smart translator here. It consists of three main parts: the encoder, latent space, and decoder. Starting with the encoder, it takes the full image and compresses it into a smaller, simpler version, kind of like summarizing a whole book into a short sentence. It then passes this summary into the latent space, and from there, the decoder takes that summary and tries to rebuild the original image. All that helps the model learn the important features without memorizing every single thing. And finally, we have the FNO, or the Fourier neural operator. It has nothing to do with Oreos, by the way. That one helps the model deal with more complex patterns by transforming the data into a different form that is easier to understand. It's like switching to a different language that makes complicated stuff simpler. It's really useful when the data in the latent space has tricky or hidden relationships.
Ooh, so it's like giving the computer a superpower. Tell it what you want, and it draws it for you. But hold on, how do you know this thing actually works?
I'm glad you asked. So once our model generates a design based on the properties we want, I turn it into a 3D structure. We then print and test it using a tensile testing machine. Basically, the machine stretches the material until it breaks to check its strength. And from there, we can compare the properties we want to the actual properties of the material we built.
If that isn't science magic, I don't know what is. But why go through all this trouble?
Well, because these materials have endless possibilities. One important application is building antennas that help submarines communicate underwater more clearly. By designing materials with properties suited for undersea environments, we can make submarine missions safer, more reliable, more effective, and ultimately support advanced communication systems beneath the ocean's surface.
Jury hasn't built the antenna yet, but she's creating the tools that might make it possible. And that's how students like Jury at NYU are shaping tomorrow's solutions. From the Composite Materials Lab, this has been Jury's Summer.